All right, so section 1.3 is an ideal geometry. So there's just a lot of notes today. There's not a lot for you to necessarily write in, just a lot for us to talk about. So, because we're just kind of talking about the history of geometry. So first of all, that Greek mathematician Euclid was the first to organize known geometric properties and principles into a geometry. Okay, and geometry is just an orderly, systematic body of math knowledge. Man, these notes are pretty hard to read, aren't they? I have to do something about that. Okay, so Euclid is called the father of geometry, and Euclidean geometry is still used today. It's a fun word. That's what we use. All right, so then the next thing, the first blank there are postulates and axioms. So right here we have postulates, or you might hear it, the old term was axioms. It's an older term anyway. So these are the basic relationships that are assumed true without proof. So these are the basis for the theorems that we're going to learn today. And the next up are theorems. Theorems. Okay, so theorems are statements that are shown to be true by a proof, which is what geometry is all about. Okay, because a proof is a logical progression of reasoning. So the proof of a theorem can use definitions, you can use postulates, and you can use previously proven theorems, stuff that you already know. So there's kind of this geometric system over here that you'll see. Okay, so it starts down here at the bottom. We have to have, and it builds up like a tower. So we can, when we're doing a theorem, we can use undefined terms, or we don't really, there's three, but undefined terms that we will talk about. Then we have definitions. There's a whole bunch of definitions. You can use definitions, postulates. There's about 24 that we'll learn, and then you have theorems, and there's a whole bunch of those as well that we'll use this year in our proofs. So all those things. Okay, next up then, we're going to talk about the 3 characteristics in a set of postulates. Okay, so 3 characteristics in a set of postulates. Okay, so it's basic assumptions should always be that it's consistent is the first one. Okay, so it's consistent. So if postulates do not contradict one another, that's important. Okay, if we have 2 postulates of a system and they had opposite meaning, then it would be inconsistent. We couldn't have those. And that's going to look at example 1 when we do it is going to be an example for us to look at about consistency. All right, the next one, the next characteristic is independent. Everything like crammed together. Independent. So it's independent if no postulate can be deduced or proved from other postulates in the system. Therefore, every postulate is necessary. And that's going to be an example 2 is going to be helpful for that. And the last one is complete. The last characteristic is complete. All right, so if it forms sufficient base for a full description of every statement within the system, it can be proved or disproved from the postulates. All right, now I love this little star notation down there. Okay, every useful postulate system in math, because there are actually more than one. Like there's a Euclidean geometry, but there's also some other types. There's a little bit more information in your book. We're not going to study that a bunch. But every single one is consistent. Some are independent. None of them are complete. Okay? And it's limited because they're strictly human attempts to describe creation of God. And the only way that they could be complete is to God. Like we don't have all the information and all the knowledge to actually come up with a complete postulate system. And so I think that's pretty cool, and not something that is ever discussed about and talked about in your regular math system. It's only ever talked about in a Christian system of studying math. So that's pretty cool in my book. All right, so flip on over to the other side of your notes, and let's look at this example one. So determine if the set of postulates is consistent. All right, so postulate one. If two lines intersect, then every other line in the plane intersects one of them. Okay, and postulate two. If two lines intersect, then there's exactly one parallel line to both. So is that consistent? So if you need to go back. Okay, say that again. There could be, but a postulate means like this is true, right? So a postulate, if we look back, it's the basic relationships that are assumed true without proof. So there doesn't have to be more. This is just saying if there's any two lines that intersect, then every other line in the plane intersects one of them. Okay, so you think that's true?
I don't know. Like that's what I don't get it. This isn't numbers, so it's not helping.
I know, right? It's true. Okay, so if we kind of think about it, so we have a plane, okay, and if two lines intersect, so we have a line here and a line here, then every other line in the plane intersects one of them. Okay, you think that's correct. Okay, that's good. However, like I'm just trying to draw you a picture to help you because they could intersect in different ways. How about if two lines intersect, then there is exactly one parallel to both. So how do we bring parallel lines into this? Or, so, and here's the question. It goes back to, are they consistent? Right? That's the question. Are these two postulates together, this set, consistent? We go back to consistent. That's okay. If the postulates do not contradict one another.
They do contradict each other.
Okay? Caden says they contradict each other. Tori, Lucas, what do you guys think?
I have no idea.
Okay. So, do you agree with the picture that I drew? If two lines intersect, so we drew a picture of two lines intersecting. Okay. Then every other line on the plane intersects one of them. Okay, so this is saying if I draw, right, if I draw any other line on the plane, no matter where it is, and these go on, right, it's going to intersect one of them. The other one is saying, right, that there is exactly one parallel that to both. There's exactly one line parallel to both. Well, parallel.
That can't work. If they're intersecting, they're going different angles, which means that one parallel line would have to break into two angles, and that's not possible for one line.
Okay, so intersecting and parallel don't really mix. Yes. So this one is contradictory. So they contradict each other. So are they consistent?
No.
Good. So not consistent. Excellent. They contradict each other, so they are not consistent. Very good. Okay, so let's look at the next one, which is an example of independence. So, sorry, I probably should delete before I move it up, but. All right, so example 2. We're determining if they are independent this time. So before we even start, let's look back at the definition of independent. Independent says postulates, or no postulate can be deduced or proved from other postulates in the system. Therefore, every postulate is necessary. So
technically, they have to contradict each other?
No, we don't want them to contradict.
Oh, we don't want them to?
Mm-mm. No, because we want it to be consistent and not contradict. Okay, but now we're looking at independent. Is every postulate necessary? All right, so okay, so now because we're kind of switching gears to looking at independence. So postulate 1, if an animal is named Polly, then it is a parakeet. Okay. Postulate 2, if an animal is a parakeet, then it's a bird. All right. If an animal is a Polly, then it's a bird.
Well, 3 contradicts the first two, but postulate 1 doesn't necessarily mean that.
Okay. Say that again for me.
So postulate 3 contradicts postulate 1 and 2 because it mixes them together.
Okay, postulate 3
Oh,
mixes.
but technically it's just like taking out a step. Because a poly is a bird.
Okay.
It's a parakeet and the parakeet's a bird. So you just took out the parakeet step.
Okay. So independent, if we look at the definition again. If no postulate can be deduced or proved from other postulates in the system. So you're saying that 3 is just a conclusion of 1 and 2.
Correct.
Right? So then if that's the case,
It's not independent.
it's not independent, right? Because this postulate 3, is not necessary. It is not necessary. We already had that conclusion. Or like we could get that. It's just the logical conclusion of postulates 1 and 2. So 3 is not necessary. So this is not independent. I promise it won't always be this hard.
No. I promise that.
Okay, the next up is an incidence postulate. The incidence postulates. This is, again, a lot of vocabulary today, getting us started. Okay, so the incidence postulates are those first postulates in geometry. And incidence is a point that's an incident with a line, falls or lies on the line. So it's just saying, it's like when a point is on a line. But the entire structure of geometry is built on these incidence postulates and some others. So there's like 4 or 5, I can't remember. There's around 5. 6 is what this book has. Other textbooks use 5. All right. But they are called incidence postulates. Then you need to know that 1 and only 1 is the same thing. It's equal to exactly 1. Because you're going to see that in our postulates, in our theorems, in the way that they were written. You're going to see 1 and only 1, 1 and only 1, 1 and only 1, a lot. So, all right, we good? Okay. Then next up is the incidence postulates. Hopefully you enjoy my drawings. Okay, so the first one is the expansion postulate. Oh, hold on. I need to move this down so you can see point D up there. Okay, I almost forgot about it. Okay, so the expansion postulate, and the notation is there, the P1.3.1. So you know it's in chapter 1, section 3, and it's the first postulate listed. That's how they're notated in your book as well, so you can find them there for reference. Okay, but the expansion postulate says a line contains at least 2 points. Okay, a line contains at least 2 points. A plane contains at least 3 non-collinear points. And space contains at least 4 non-coplanar points. All right, so if I look at my drawing up here, what's my line? I need 2 points.
Line K.
Line K would give me 2 points off that line.
A and B.
Okay, so I would have line A and B. Okay, great. So line A and B would be there if I was going to name it. To name a plane, I need at least 3 non-collinear. Non-collinear means
Not in the same line.
not in the same line. So this would be plane A,
A, C, and D.
A, C, B.
But they're on the same line.
No, C is not on that line.
A and B are.
A and B are, but the third one is not on the line, so that's okay. That's a good question. Okay, because D is actually space. Because space contains at least 4 non-coplanar points. D is not on this plane. So if this plane if this plane is here that has A, B, and C on it, D is up here. It's a different plane. Okay, if I look at it like that. So my 4 non-coplanar parts, or space would be A, B, C, and D. Okay, so then I get into space. All right, lots of fun. The line postulate. Okay, the line postulate is any 2 points in space lie in exactly one line. So any 2 points in space lie in exactly one line. Exactly one means one and only one. So I could connect, if I was looking back up here at this plane, I could connect A and C, right, with one and only one line. I could connect, if I wanted to connect B and C, it would give me one and only one line. I couldn't draw multiple lines through there. Does that make sense? Okay, so that's what that line postulate tells us. Okay, a plane postulate is 3 non-collinear points. What's non-collinear mean?
Not in the line.
Good, no, so not in a line. So plane postulate, we have 3 non-collinear points lie in exactly one plane. So 3 non-collinear points lie in exactly one plane. So it's the same thing. I can't get multiple planes out of it. I just get one plane out of any 3 points. We caught up?
Yep.
All right. Then we'll go to the flat plane postulate. All right. Takes up a little bit more space. I hope I can get the definition here. So the flat plane postulate. If 2 points lie in a plane, then the line containing then the line containing those 2 points lies in the same plane. So if the 2 points lie in a plane, so let's say, again, like A and B are in this plane, okay? The line that connects those is in the same plane. That's all that's saying. Like, this is stuff that you genuinely already know, but we have to give it a name. Okay, so just like A and C lie in this plane, if we connect those with the line is in the same plane as the points. Make sense? Okay. All right. Next up, line intersection postulate is if 2 lines intersect, then their intersection is exactly 1 point. Again, stuff you already know. Two lines intersect, so we have line M and line N. They intersect at 1 point, G. They can't intersect multiple times. Treasure, have you worked on the homework assignment too?
Yes, I finished it.
Already?
Yeah.
Did you do the lesson practice from today's lesson?
Yeah, I was reading it as I was watching the video.
Okay. All right. Awesome. All right. Next up is plane intersection postulate. Okay, so if two planes intersect, then their intersection is exactly what? One line. Yes. Okay, so if two planes intersect, then their intersection is exactly one line. And so that's what I attempted to draw here. It's not the best. But so we have two planes, P and L, or P and Q, pardon me. So one's horizontal and one's vertical. And so their point of intersection is that line across there. So again, things you already know. And you're probably like, "Oh, okay, this is dumb. I get this. Okay." You feel like you might be wasting a lot of time, but this is how geometry rolls. That's how we have to start off.
Mommy, I just want lunch.
You just want lunch. That works too. Okay, are we all cut up writing? Lucas, you good? Okay. Then flip over to the back, and we'll get into a couple theorems. Our first theorem. So theorems, okay, sometimes they have names. Like, have you ever heard of the Pythagorean theorem?
Yep.
Okay. All right. Sometimes again, they'll just have this notation. So it's T for theorem, and then 1 for chapter 1, point 3, it's section 3, and point 1, it's the first one introduced in the chapter. All right. So this one, theorem T1.3.1, is a line and a point not on that line are contained in one and only one plane. Okay, so a line and a point that's not on the line are contained in one and only one plane. So if I was going to draw a plane, I could only draw one plane that would contain all of those. Okay, I couldn't draw an intersecting plane because the intersecting plane would also intersect that line. So you can also see, if you want to look in your book, there's a paragraph proof on page 13 you can look at. It's also an informal proof there. I wasn't going to copy that all down. It's not that relevant. Like, as long as you know the theorem, then I don't feel like you need to know the proof at this point. Okay, next up is theorem T 1.3.2. All right, so we have two intersecting lines. I feel like it's squeaking less. Is that me, or do you all agree? Okay, I think it's how I'm holding the pen, so I'll try to continue to do that. Two intersecting lines are contained in one and only one. What? Oh my gosh. Plane. All right, I am so sorry to keep you. Let me get this last definition in there. The next one, two parallel lines are contained in one and only one Yes. Plane.
Don't erase it yet.
Okay. So 2 parallel lines are contained in one and only one plane. And the homework assignment for tonight is section 1.3, numbers 1 through 9 odd, 2 through 28 even, 31, 34, 37, 38, and then 41 through 49 odd.
Due Tuesday?
Yes, due Tuesday.